All right, so we talked about how intermolecular forces affect the melting point and boiling point of compounds, but they also affect other properties of the compound. So let's talk about those. So the more intermolecular forces we have, or the stronger intermolecular forces we have more of some other stuff, right? So the first thing is surface tension. So more IMFs, more surface tension. So surface tension is defined as the energy required to increase the surface area. And so the way I like to think about it is you have this kind of, cup of water here. And there's a certain amount of surface area this, cup of water has. And then we're going to go ahead and throw a block in here. And then when this block gets thrown into here, what you can see is that the amount of surface area here that I've indicated in this dark blue has increased. So the harder it is to do that, the more surface tension something has. And the more IMFs that we have, the more surface tension that we have, the harder it is to do that. And so this picture right here illustrates the why behind that pretty well. So you can see this little spider's trying to walk on the water, right? So if it tries to push its leg down, you're going to basically destroy these intermolecular forces, right? You're going to break these intermolecular forces. And so since water has high surface tension, it allows this little kind of bug to walk on this water. Another property is viscosity. Viscosity is the resistance to flow, or kind of how thick a liquid is, how viscous it is. And so it makes sense that if we have a lot of intermolecular forces, we would have a much thicker liquid, right? It's going to stick to itself more. Another very important part, especially for trees and some other biological purposes, is capillary action. So capillary action is the flow up a narrow tube. And so you may notice that water will flow up a narrow tube. So this actually depends on what kind of intermolecular forces you have between the tube and the solvent, whatever liquid you have in there. So there's two main types of forces here. There's the adhesive forces and the cohesive forces. So adhesive forces are how well something sticks to other things. So how well the water or whatever is going up your tube sticks to the tube. And then the cohesive forces is how well something sticks to itself. So how good is the water sticking to itself? And same thing as like dissolves like sticks to like. And so one thing to know is that glass is a very polar compound. And so if we have this kind of glass tube here, and then if we have some water, we'd get this kind of meniscus type of thing. And that's because the water likes to stick to the glass. There's a lot of adhesive forces here that's causing the water to climb up the side of the glass because they are both polar and thus attracted to one another. If you try this same experiment, here you have glass, but instead you place something non-polar. Let's go with kind of mercury. Mercury is a non-polar compound. What would happen? Well, it doesn't want to stick to the glass. It'd rather stick to itself. And what you'd see is this kind of reverse meniscus and this kind of bubble instead, right? Because it has cohesive forces and wants to stick to itself, but it has very poor adhesive forces because it is nonpolar and the glass is polar. This picture just shows that. They're flipped from my drawings, but that's okay. You can see on the right here, we have water. And so you can see how it likes to stick and is kind of trying to climb up the glass, whereas the mercury does not try to come up the glass. Instead, it's kind of bubbling and trying to stay away from the glass due to the differences in polarity. Little fun fact for you. This is the basis of how Rain-X works. I don't know if I spelled Rain-X works, but whatever. Or really any hydrophobic surface. So hydrophobic means water fearing or water hating, so it doesn't like water. And so what they do is make a really non-polar compound. That way it won't attract any of the water. So anything that's kind of waterproof, if you have those waterproof sprays, they're basically just non-polar sprays, right? So oftentimes it looks like this. Where you have your substrate. In the case of Rain-X, that's your windshield. In case of, some kind of spray, that's your shoe. They have some kind of head group that's usually a polar group that'll let it stick onto the compound. And then they have this kind of non-polar group that will basically repel any water. And that's what this picture is showing here as well. So on the left, we have a hydrophobic surface, so it doesn't like the water. So you can see the water is kind of trying to stick more to itself than it is the surface. Whereas on the right side, we have this hydrophilic surface, and so the water is trying to spread out to maximize its contact with this polar part. Another fun example is, kind of water wicking up a paper towel. So water will wick up. In this case, they have wine, but same thing. It's the water that's going up. So it'll wick up that paper towel because the paper is made out of cellulose, and cellulose is a polar compound. So it's all about intermolecular forces. And so you can look at a compound, think about what intermolecular forces it has, and then think about what properties that that compound is going to have, and how it's going to interact with other compounds of either like intermolecular forces or different intermolecular forces.